So I'll be recording the lecture. So if you don't want to be in the recording, just send me a chat message, although it'll be difficult for me to find as I'm in this PowerPoint, but I can try. All right, so this is last time. This is not the right PowerPoint. I opened the wrong one up. All right, so this is what we're doing today. We are going over the work energy theorem. So the work energy theorem gives us a relationship between work and velocity. So here's our formula we learned last time. And remember that F equals ma, and work equals force times distance, right? So if we do this out here, we can say work net equals MAD. And if we use our equation, V squared equals V naught squared plus 2A X minus X naught, which is D, we can get V squared, sorry, where's my undo button? Where is my crazy, sorry, user error today. There it is. I don't know where that went to. If we rewrite this equation out here as V squared equals V naught squared plus 2A, and we call X minus X naught D, right? Then we can substitute in V squared equals V squared minus V naught squared over 2 equals AD. So we can take this right here and substitute it in for our value up here. So we get work net equals, right, that's the AD, M over 2 V squared minus V naught squared. And this is better written as work net equals 1/2 M V squared minus V naught squared. And this is known as the work energy theorem. This, what I just put down here right now. This is the work energy theorem right here. And this is a relationship between the amount of work done and the velocity in the system. The part of the theorem, the 1/2 mv squared, this is known as kinetic energy, right? K is 1/2 mv squared. So delta K equals 1/2 m v squared minus v naught squared. So our work energy theorem really says work equals delta K. That's the work energy theorem. The work equals the change in kinetic energy of a system. And remember we talked about last time, we said, all right, we have a positive force and we have a negative force, let's call it friction. And this over here causes positive work and this is negative work. The reason this causes positive work is because it's increasing velocity, right? Our delta K is positive. This over here decreases velocity. Our delta K is negative. And that's why we have a negative work and a positive work. See how that works? So that's the idea behind the work energy theorem and how it relates, just our definitions. So we're going to try some different problems here. It says, suppose a 30 kilogram package on a roller belt conveyor system is moving at 5 meters per second. What's its kinetic energy? So here we have just a simple problem where we have a 30 kilogram package on a roller belt conveyor, and we just want to find its kinetic energy. So let's write down what we have. We have the mass. That's equal to 30.0 kilograms. we have the initial velocity, or the velocity is 0.5 meters per second. And all we're doing is looking for the kinetic energy. K equals 1/2 mv squared. K equals 1/2 times 30 times 0.5 squared. Calculator, so many of them. 3.75 joules. That's the kinetic energy of this object. Seems simple, I hope, that part. Any questions there? All right, let's try another one. I already went over that slide, the work energy
Actually,
theorem.
do you have a question?
Sure.
Okay, so you know how like, you gave us the videos? Which video are you going over?
Work energy theorem. I'm not sure which of the videos. I think it's
it was
C.
video C.
I think it's C. I think I screwed up. That's what I was saying earlier in the class, that I have to go through and edit those.
Oh, okay, because I went over video B like before class, so that makes a lot of sense.
Sorry about that. I forgot to do
Yeah,
that.
I just went up to B, so this looks like semi-familiar.
Oh, good. Hopefully we'll hit something familiar. All right, so this is the work energy theorem written out. We already went over that. So let's do some more problems. This is number 12 out of the book. It says calculate the force needed to bring a 950 kilogram car to rest from a speed of 90 kilometers per hour and a distance of 120 meters. All right, so we got the mass of the car equals 950 kilograms. The initial velocity is 90 kilometers per hour. The final velocity is 0, right? It's bringing, oh, why did I put a V naught? The final velocity is 0. And the distance is 120 meters. So we got to change from kilometers per hour into meters per second. So 1 kilometer, 1,000 meters, 1 hour, 3,600 seconds. That gives me 25 meters per second. So this is calculate the force needed to bring it to stop. So this is the work energy theorem. Work equals delta K. FD equals 1/2 mv squared minus v naught squared. Oh man, I did that wrong. Look at that. Our goal is to find F. So F equals mv squared minus v naught squared over 2d. F equals 950 times negative 25 meters per second squared over 2 times 120. I got 2.474 or 2.47, I'll just say 2.474 newtons, and it's negative. It's bringing it to stop. And you see how these negatives are still working together with the velocities and the accelerations, and the signs are all up to date. Part B says, suppose instead the car hits a concrete abutment at full speed and is brought to stop in 2 meters. So now, instead of this 120, right, instead of 120, we have 2 meters in denominator. So the force is going to be how many times bigger? Right, we can say F equals, we can do it out, 950 times negative 25 squared over 2 times 2. And essentially, it's just going to be 60 times bigger. So in this case, I get 14640 newtons negative. So you get a much bigger force when you're coming to a stop in a much shorter distance. Any questions there? All right, here we go. Boxing gloves are padded to lessen the force of a blow. Calculate the force exerted by a boxing glove on an opponent's face if the glove and face compress 7.5 centimeters to below, in which the 7-kilogram arm and glove are brought to a rest from an initial speed of 10 meters per second. All right, you guys tried part A. At your seats, this part A. Give that a rip. And again, I can't see what you're doing because of being on the PowerPoint instead of the Zoom. So just have to hope for the best here. Try to time it best I can. All right, we have an idea what we got going on there?
Yep.
All right.
Pretty sure I got it.
Good, good. Here we go. Calculate the force exerted by the boxing glove. So it's pretty close to what we did last time. FD equals 1/2 mv squared minus v naught squared. So we got 7.5 centimeters of distance. So that's 0.075 meters. The mass is 7 kilograms. The initial speed is 10. And the final velocity is 0. So we want to calculate the force pretty much exactly like we did last time. It's going to be 7 times 0 minus 10 squared over 2 times 0.75. And you get 700. You get a pretty big force hitting your face, right? 466.6 newtons. I'm gonna guess that's a repeating decimal. Then it says calculate the force if you're hitting them with your bare knuckles. So again, do the same thing we did last time. We're not gonna do this because we really just did it. So you just put 2 down here, right? 0.02 instead of 0.075. And that's how you solve that problem. So, I mean, that's 3 times bigger. 3.5 times bigger, almost even. So that's a lot of force hitting you in the face. The next thing we're going to talk about is power. Power is the rate that work is done, how fast we do our work. That's our power. This is what your lab is on, and we're going to do a lab today, or do a problem today that's like your lab. So it says the SI unit for power is the watt, where 1 watt is 1 joule per second, and here's your conversion. And most of you guys in electrical and electromechanical probably know that conversion pretty well. So we can look at this in a couple ways. Power equals force times distance over time, right? That's work. Power can equal the change in kinetic energy over time. And we can expand these things, right? We can have MAD over T. We can have 1/2 M V squared minus V naught squared over T, or essentially mv squared minus v naught squared over 2t. It's a t, not a 2. But that's your idea here, is that you can manipulate these two equations to solve for a lot of things. So essentially power equals work over time, and our units are watts. This is a 15 kilogram race car, can go from 0 to 90 kilometers per hour in 5 seconds. What's the average power required to do this? So, okay, so we got the mass of the car is 1,500 kilograms. The initial velocity is 0. The final velocity is 90 kilometers per hour. And that's 25 meters per second. We just did that a few problems ago. And our time is 5 seconds. And our goal is to find the average power. So for this case, power equals work over time, and we're going to use delta K over T, right? Because work equals change in kinetic energy. So power equals 1/2 M V squared minus V naught squared over T. Power equals 1,500 times 25 squared over 2 times 5. And we get 93750 watts.
Can we just sit here for a second so I can figure out what's going on?
Sure. Does anybody have anything they need clarified while we're waiting here for a minute?
I'm good.
Anybody have anything clarified? Now, if we wanted to find out how many horsepower it was, we could just divide by 746, right? And that would give us our horsepower. So that'd be 125.67 horses. Not a very strong race car, right? 125 horsepower.
That's a 4-cylinder. It's yep.
Yeah, my father-in-law's got a Shelby that has 850 horsepower in it. Right? That's a race car. This little thing. Is that your Fiat you're driving around, Ken? All right. Suppose you push a 30-kilogram package with a constant force. What's 4 there? Package 4. I think that's a typo. With a constant force of 120 newtons through a distance of 0.8 meters, and that the opposing friction force averages 5 newtons. Find the speed of the package at the end of this push. All right, so in this case, we know the mass is 30 kilograms. The force is 120 newtons, right? So if we draw a free body diagram, we have an applied force of 120 newtons. We have a friction force of 5 newtons. So I don't want to write the force as 120, do I? What do I want to write the force as?
$115.
115. Good. We want to do the net force. So we want to say the sum of the forces equals 120 minus 5. The net force in this case is 115 newtons. And that's what we learned last chapter, right? So now we have the force. We have the distance is 0.80 meters. And we know it starts from rest, and we want to find the final velocity. So we're essentially doing the same thing here. Work equals delta K. FD equals 1/2 M. This should probably be in the other section. I don't know why this is after power, but it's a good review. And then we're trying to find this final velocity. So we got 2FD over M equals V squared, because V naught's 0. So V equals the square root of 2 times 115 times 0.8 over 30. .45 meters per second. Anybody need anything clarified there? I'm not sure why this is at this point in the lecture. I kind of screwed that up, but it's okay. All right, now we got a power problem. What is the power output for a 60-kilogram woman who runs up a 3-meter high flight of stairs in 3.5 seconds? This is going to be like your lab, your power lab. This problem. Pretty easy. So power equals work divided by time. This is work, not weight. So if we're going upstairs, remember work has to be in the same direction as the force. So the force is the person's weight, mg. So the work in this case is going to be the force, mg, times the distance over the time. So that's 60 kilograms times 9.8 times 3 divided by 3.5. $504 watts. 504 watts. We have to have the vertical height. When you measure your stairs for the lab, do not measure this height. You got to measure the height of one step. You find that distance, and then you multiply it times the height of the stairs, 4D or whatever. You're going up to bleachers at school, 20D. So you have to have the vertical because the force is vertical. They have to be in the same line. So remember that when you do the lab. Do you have any questions on that?
So we like take the stairs, we measure each stair and add them together.
Well, yeah, you measure the height of one step. So you take your tape measure, you measure the height of one step. Let's say it's what? 6 inches? And then if your staircase is what? 10 steps high? The whole height of your staircase is 6 inches times 10 stairs, 60 inches. Does that make sense? Yes? No? Maybe?
Yeah.
Yeah? All right. All right, let's try this here problem. This one's kind of tricky. It says if a person who normally requires an average of 12,000 kilojoules of food energy per day consumes 13,000 kilojoules per day, he will steadily gain weight. How much bicycling per day in hours is required to work off this extra 1,000 kilojoules? There's a table in the book, table 7.5, that tells you bicycling uses 400 watts or 400 joules per second, right? A watt is a joule per second. So bicycling, the power is 400 joules every second. So if we put that in terms of kilowatts, that'd be 0.4 kilojoules per second, or kilowatts. Follow me? So for this problem, we say, okay, the power is the work over time. We're given the work is 1,000 kilojoules over time. Our goal is to find this time. So we take 1,000 kilojoules and divide it by 0.4 kilojoules per second. That gives me 2,500 seconds. So we can convert that. There's 60 seconds in a minute. Oh, 3,600 seconds. Let's go with 30. We're doing it in hours, right? So 3,600 seconds in an hour. Oh, I don't want to highlight. $3,600 seconds in 1 hour. So that gives me 0.7 hours. I should have made it in the minutes, which is 42 minutes, right? 60 times 0.7 or 0.6944. Follow me there?
Says 42 minutes.
Yep.
All right.
Anybody else have any questions or anything? All right, let's try the next one. How long will it take an 850 kilogram car with a useful power output of 40 horsepower to reach a 15 meter per second, neglecting friction? You guys try this one at your seats. All right, let's give this one a try. See how we did here. How long will it take an 850 kilogram car with a useful power output of 40 horsepower to reach a speed of 15 meters per second? So the mass of the car, 850 kilograms. The power is 40 horsepower. And we're going to change that into watts for our calculation. So that's 2984. I'm just going to write it out. 2.98 times 10 to the fourth watts. And our final velocity is 15 meters per second. Our initial velocity is 0. So again, we're going to use our delta K formula. P equals delta K over T. So that's mv squared minus v naught squared over 2t. P equals 850 times 15. Oh, excuse me, we're looking for time. Let me redo this. Our goal is to find the time, how long. So we want to rearrange. T equals mv squared over 2p, because v naught is 0. So T equals 850 times 15 squared over 2 times 2.98 times 10 to the fourth. And T is going to equal 6.4 seconds, 6.41 seconds. How'd we do there? Did anybody have any questions or anything? All right. I got a lot of these in here. Let's do this problem here. What is the cost of running a 0.2 kilowatt computer 6 hours per day for 30 days? If the cost of electricity is 12 cents per kilowatt hour. So this is essentially just a factor label problem. You can set this up. So let's see if we can figure this out. The cost of running this computer. Try this. All right, let's give this a try. We are going to try to find out what's the cost. Our end goal is $, the almighty dollar. That's what we're trying to solve for here. So we can start off with 0.210 per kilowatt hour. Now, when you have a house and you're paying for electricity, it's measured in kilowatt hours. So we got to get those both out of the denominator. So we have 0.200 kilowatts and 6 hours per day and 30 days. So we just multiply the top through, and that gives us how many dollars we are cost to run our computer. So 1 month costs $4.32 to run your computer for a month, 6 hours a day. So sitting at home doing these Zoom meetings for 6 hours a day, you're spending $4.32 a day, $25 a week, $100 a month, right? Now, I doubt you're doing enough computing to really run it that hard, and you're probably not on it 6 hours a day, but I'm sure you guys are running electricity that much. Any questions there? All right, efficiency is how the percentage that you use it, your work, so like 90% efficient, right? We don't leave it in the percentile, that's 0.90. The efficiency is 0.90. So that means the energy input times 0.90 equals the work that you're actually getting out, like a motor. A motor that's 90% efficient isn't going to do the same amount of work. It's going to give you less work. So a 5 horsepower motor at 90% efficiency is actually only doing 4.5 joules of work. So this is something you guys should be familiar with. And here are just the, what's that?
Oh, I couldn't see what you wrote down, but I think I understood what you were saying.
Can you not see it?
It's like below the.
Oh, it's below. So like the energy input at 90%, so that'd be 0.9.
Yeah.
Is equal to the work output. So if you have a 5 horsepower motor or a 5 joule motor, I guess I should be in horsepowers, not joules, at 0.9, right, you're getting 4.5 horsepowers out.
Okay.
You're not getting the full thing.
I see.
And this is just a chart. I don't know why I have this in here from the book, but this one's kind of tricky. It says water is lifted out of a well 30 meters deep by a motor rated at 1 horsepower. Assuming 90% efficiency, how many kilograms of water can be lifted in 1 minute? So our efficiency is 90%. So the power is 1 horsepower. So the power is equal to actually 0.9 horsepower. That's all we're getting out. So we're going to change that into watts. If I can do it. Oh man, that's not the eraser. Change that into watts. So 1 horsepower has 746 watts. So we'll just put that out, 0.9, 746 times 671.4 watts. We know that our distance is 30 meters. The time is 60 seconds. And if we draw a free body diagram of the water, right, the force is equal to the weight, mg. And our goal is to find this here mass. So we have dt in power. So power equals work divided by time. Power equals force times distance over time. Well, the force is going to be the weight of the water, mg. Our goal is to find the mass. So we cross multiply PT over GD equals M. So 671.4 times 60 seconds over 9.8 times, what's the depth, 30? That gives us our mass. 137.02 kilograms. It's kind of tricky. Are there any questions there? Got a lot going on there. It's a good example of all of them combined, really, all of the stuff we learned today. One more and then the quiz. I don't really like this problem anyway. I think we're just going to jump right to the quiz. Anybody have any questions here before we go to the quiz?
I wasn't here last time because I didn't get that email in time to know like that we had to be here. So do I just go over to the portal and then take the quiz? Like, how does this quiz work?
This quiz? You just take it right now and then you'd send me a chat of the answer.
Oh,
A
okay.
private chat message. Who is this? Oh, I don't know who's talking, but
Sorry, it was Jonah.
if you go and look through that other video at the end, I put the quiz on there. You can just do it and then email that to me. But in the future, I won't let that. But I know the first one was kind of last minute, so I'll
Okay.
take it. You know what I'm saying?
Yeah.
I have a quick question for
Yeah.
it's power equals work over time, which is also like FD over time, which is also like, I'm just trying to like,
Well, yeah, that's what we talked about way back in the beginning. The
Yeah,
power
yeah.
can be a bunch of different things, right?
those are all,
different things.
those are all separate things. I'm just trying to,
They're all the same, but they're all just a different way of looking at it.
okay.
You know what I mean?
It's like, yeah, they just mean different things. Okay.
Does that make sense?
Yeah.
All right, let's take this here quiz. Quiz 13. A car's bumper is designed to stand a 1.1 meter per second collision with an immovable object without damage to the bottom of the car. The bumper cushions the shock by absorbing the force over a distance. Calculate the magnitude of the average force on a bumper that it collapses 0.2 meters while bringing a 900 kilogram car to rest from that initial speed. So, when you are done, chat me the answer. Sorry, I gotta stop the recording. I'll go back.
Okay.